All right, we are going to be looking at air friction and terminal velocity. This is in the notes packet for the introduction to Newton's laws. And we're going to be, in this video, working through 8, 9, 10, and 11. So, a couple things to start off with. Whenever an object moves through air, it experiences air friction. And air friction always points in the opposite direction in which the object is moving. Okay, so if the object's moving left, the air friction or air resistance vector would point right. If it's dropping down, the air friction or air resistance would point up. So it's always opposite of your direction. Just like friction always resists the motion for a sliding object as well. So there are 4 factors that will determine the amount of air friction an object feels. First one is size. Okay, so think of if you have 2 balls that are the same mass, one's larger, one's smaller. You can think of that larger ball. You can think of that larger ball running into more air molecules. Okay, so that's what you got to think of when you think of these things: is what is the amount of air molecules that these objects are going to be running into as they fall. So larger objects will obviously hit more air molecules as they fall, and that will cause a greater resistance. Shape is also a factor that affects air friction. Think about, I don't know, a skydiver. So if you have a skydiver that's falling kind of flat compared to a skydiver that's falling straight down, that's their head right there, which one do you think will experience more air resistance? The one that's flat. Why? Because of the shape. Just think about how many air molecules will be hitting this guy as he's falling compared to only a couple on this guy on his head. Density of the air as well. So if the air is colder, if you're more towards the surface of the Earth, you will be contacting more, again, air molecules. So the space station is an example. The space station is orbiting the Earth high up in the atmosphere. The density of the air is so small up there, it's barely hitting any air molecules, so it barely has any air friction at all. And the last one is the speed of the object. The faster you're falling, the more resistance you will feel, because the more impact you'll have on the air molecules there. So we have a situation here. Someone's dropping a ball off a cliff, and I'm going to draw the free body diagram of the ball in each of these spots. And I'm just going to draw the ball as a dot, rather than we usually been using it like a square. And I'm going to be finding the net force in the vertical direction. Okay, so what I'm going to do here is I'm going to say it's greater than, less than, or equal to 0. Okay, again, if it's pointing down, it's going to be less than 0, right? It's going to be a negative. If your net force ends up pointing up or 0, it'll be positive. So let's take a look here. So right away, right when I drop the object, it's not moving. Okay, however, it does have a gravitational force pointing straight down. There is no air resistance because it's not moving. So my net force in the y direction would be obviously less than 0 here. Why? Because it's negative. This is the only force acting on it. It's a negative force, so it's going to be less than 0. As it starts to fall, the weight force, remember, is constant, so this will be the same as that. This is still a wave force. However, I'm starting to move, so I will have a resistance force starting to grow, and that's going to be pointing up. Called force of resistance, F sub R, we could say F sub F. Actually on here, I'm going to change that to F sub F. Force of friction, air friction, either one's fine. I'll leave it as resistance. So, if you notice, I'm still accelerating because I know my net force is still pointing down. You notice my weight force is still larger than my resistance force. So my net force in the y direction is still going to be less than 0. Okay, but as I move faster, this resistance force is going to start growing. It starts at 0. There is no resistance force, air resistance. As it starts to move faster, the resistance starts to grow. You can think about when you're driving in your car, or you're driving in a car and you're going 30 miles an hour and you stick your hand out the window. You can feel the resistance compared to when you're going 70 miles an hour and you feel the resistance. When you're going 70 miles an hour down the freeway, you feel a greater pushback from the air resistance. This is kind of what's happening. The faster you move, the more air molecules are impacting your hand, or in this case the ball, and the greater the resistance. So when it does reach terminal velocity, a terminal velocity occurs when the net force is zero. And terminal velocity means the object stops accelerating and it falls at a constant speed or a constant velocity equal to what's called the terminal velocity. So here's my weight again. I'm meaning to draw these vectors the same here and in each of these situations. However, now my resistance force has grown so much that it is equal and opposite to my weight. That's going to be the same length as well. Call that force of resistance. It's equal and opposite now. So what does that mean? That means the net force at terminal velocity, so the net force in the y direction, is equal to 0. If the weight is 5 newtons, the resistance force would be 5 newtons, and it would cancel out. Okay, so here are the three situations. Okay, it's weight less than 0, the net force is starting to approach 0, and now it's 0, and it's going to fall at a constant rate. And this rate is called terminal velocity. In this case, the acceleration is 0, the net force is 0. So when your acceleration is 0, you're not speeding up anymore. All right, so let's turn look on the bottom of the page here. So here are two questions that we'll have with this. Let's see if I can zoom in a little bit on here. That's a little too much. Well, let's be good enough. We'll see what I can do. Two balls of equal weight are dropped, but one is twice the size of the other one. So we have a situation here. We have two balls, one large one and one small one. Okay, there they are. We'll say ball 1, ball 2. They have the same weight. Okay, so they're the same weight. So the FG for both of them is going to be the same. Try to draw this straight here. Okay, so these are equal to each other. Okay, which one reaches terminal velocity first, and which one reaches the ground first, and why? So let's think about this. We drop both these balls. They're not moving. They start to move, and at some time before it reaches terminal velocity, the resistance force is going to start to grow on both of them. And you ask yourself, which one is it going to grow faster on? Which one's going to be impacting more air molecules, the smaller one or the larger one? What's going to happen is this larger one is going to impact more air molecules. Okay, so this one will grow faster than this one. So after, I don't know, let's say a second, this one will have a large resistance force, while this one will have a small resistance force. Okay, and they'll get to a point at some point in time where this force, the resistance force here, will be equal and opposite to the weight. Okay, and at that point, this force will be smaller than the weight. So ball 1 will reach terminal velocity first. Okay, so at this point in time, I drew right there the terminal velocity, okay, of 1 will be less than the terminal velocity of 2. So what's happening? So which one reaches terminal velocity first? Well, because terminal velocity 1 will have a smaller terminal velocity. Okay, the larger ball reaches, we'll call it V sub t, terminal velocity first. Which one will reach the ground first? Well, you gotta ask yourself, well, since this one now is, ball 1 is moving at a constant speed, ball 2 is still accelerating because the weight force is greater than the resistance force. Okay, ball 2 will get to a higher speed. And because of this, okay, it will reach the ground first. So the smaller ball reaches the ground first. Why? Well, 1, it accelerates longer because the resistance force grows slower for it. It accelerates longer, which means it'll have a higher velocity at the end, and it'll be reaching the ground first. Okay. Second situation is a little bit different. We have two balls that have the same size now, so it's a little bit different. Okay, so let's take a look here. So they have the same shape, but let's say one is solid iron and the other one is like hollow aluminum. Okay, so they have the same shape. We'll say ball 1 and ball 2. However, let's say ball 1 is a lot heavier, which means its weight force is a lot larger than ball 2. Oops. Sorry about that here. Let me fix that. Okay, so what's happening here? There we go. So the weight force for ball 1 is a lot larger than the weight force for ball 2. However, they're the same size. So what's going to happen is the resistance force for both are going to grow at the same rate. Okay, so it's getting larger, it's moving faster. The resistance force is going up for both. Okay, and eventually we'll get to a point in time where this resistance force is equal and opposite to the weight force over here. And at this point, the acceleration starts to equal 0, which means it doesn't speed up anymore. While at this point in time, ball 1 is still accelerating. So which one reaches terminal velocity first? We'll say ball 2 reaches v sub t, terminal velocity first. Okay. And which one reaches the ground first? Well, similar to this first problem, which one reaches the ground first? Well, since ball 2 stops accelerating and moves at a constant speed, ball 1 is still speeding up. Ball 1 will end up with a higher speed because it accelerates longer. Because of this, it will hit the ground first. So ball 1 reaches the ground first. Why? Just like in situation 1, it accelerates longer. Because it accelerates longer, it ends up with a higher final velocity before it touches the ground. So this should make sense. Just ask yourself, which one is in contact with air molecules? Okay, in a case where they're the same shape, you gotta ask yourself, okay, well, if they're the same shape, then the resistance force is going to grow at the same rate, and which one reaches this terminal velocity first, whereas the resistance force equals the weight. Alright, I hope that makes sense. We have about a minute left here. I'll take a look at number 10 and 11 as well. Alright, so these two questions deal with inertia. Inertia is, guys, you need to understand this, is the resistance, okay, the resistance of an object to change its motion. Another way to say that, guys, is it's the resistance of an object to accelerate. Okay? So if it's not moving, it wants to stay not moving. If it's moving in a straight line at a constant speed, it wants to keep doing that. Okay? The more mass it has, the more it resists its change in motion. So something that's more massive, okay, like a garbage truck, resists change in motion more than like a small smart car. Okay? And you can see this a lot. This is why in football running backs are generally small, because they can change motion very quickly, and linemen are big because they don't want to change the motion. If they're not moving, they want to stay not moving and block. Okay, so it's a function of mass. So the more mass something has, the more it resists change in motion, the more inertia it has. Why does an air hockey puck keep moving on an air hockey table once it has been hit? Well, on an air hockey table, okay, the puck is actually hovering above the table. There's little pockets of air shooting the hockey puck up to create a situation in which the friction is very close to 0. We can assume that the air friction is 0. So once you apply a force to it, it's going to keep moving in a straight line at that constant speed forever until it hits the side of the air hockey table. You see this in things in space where there's no air resistance. They shoot a spacecraft off and it will continue straight forever. Number 11, how can you use inertia to your advantage in sports, and when is it to your disadvantage? Well, if you want to change directions, you want to be small. If you don't want to change directions, you want to be massive. So there you go. That's all the time we got here for this. So if you have questions, let me know. Thank you.